So the topic for today is model-based system engineering demystified, and I came up with that topic because I go to a lot of places, I talk to a lot of people about model-based system engineering, and everybody gives me a different answer of what model-based system engineering is. So I started thinking about what is really model-based system engineering and where's the state of model-based system engineering today, and I want to share my thoughts with you. But before we get into model-based system engineering, we have to really talk about the reason for model-based systems engineering, and that's because of the state of systems engineering today. And I argue that the most significant challenge facing systems engineering today is how to deal with the increased complexity. And systems are getting larger in some cases, and they're becoming complex in just about every case. So I like the photos in this on this slide. The bottom photo is the RMS Titanic, the most advanced ship of its day, superimposed on the oasis of the seas, and 225,000 gross tons is the largest cruise ship today. So vastly different in size, vastly different in complexity, but systems don't have to be larger to be complex. So, for example, a 1950s era TV with a huge vacuum tube and a cabinet that holds it's actually a piece of furniture in your house, right? That was probably larger than the smart TV of today, right? But the smart TV of today is clearly more complex, but the smart. So we have to be able to represent that complexity somehow, and we have to be able to represent it concisely. And we all know that we are now working in a digital era where we have larger and distributed teams. So, for example, look at this webinar. People from all over the place on this webinar, right? You know, and that's pretty much the environment that we all work in. We all work on distributed teams, and we have to have a way to share that information across distributed teams. I know when I was a chief architect, I had some of my teams here in Virginia, and some of my team was like in California, right? So we have to have a way to share that data across it. We also have to have a way to look at emergent behavior and to model emergent behavior. And I think we could do a little bit better job of that in the systems engineering community, maybe that we have in the past. So model-based system engineering was the term model-based system engineering was defined by INCOSE like circa 2007, if I have my date right. And but we look at this definition, it captures the life cycle perspective that we should always have as systems engineers, but it doesn't give any indication of how to progress past there, it doesn't give any indication of how model-based system engineering is different than traditional systems engineering. In fact, I argue that going back to the founding of systems engineering, we have been working with models, right? Whether those models are diagrams or whether those models are matrices or requirements, they're essentially models. So this definition, well, I believe it started a discussion back in 2007 on model-based system engineering. It really doesn't help us to implement or maybe even further understand model-based system engineering, but it does start the discussion. So I have at Naval Postgraduate School, I have the luxury of going around and talking to a lot of people, a lot of organizations about model-based system engineering, and a lot of people say, yeah, we're doing model-based system engineering. And I always ask the question, well, what does model-based system engineering mean to you, right, and to your organization? And I hear different things from different places, right? So I hear things like model-based system engineering is the system modeling language. Model-based system engineering is unified modeling language, or maybe even model-based system engineering is lifecycle modeling language. Right? So the last two letters in each one of those acronyms, ML, for modeling languages. So that's what they are. They're modeling languages. A component of model-based system engineering but not a complete view of model-based systems engineering. Other people say that model-based system engineering is the Department of Defense architecture framework, or that it's the unified architecture framework. And you know, that's a component of model-based system engineering, but it doesn't tell the full story. So I call those things presentation frameworks. And then some people say that model-based system engineering is Magic Draw, or model-based system engineering is InterSlate, or whatever your favorite tool is. And if you're a tool vendor, I suppose that having the name of your product synonymous with model-based system engineering is a good thing. But holistically, what you're providing a product that is a modeling tool that is probably based on language and was able to represent data in some sort of framework. So the purpose of this presentation is really to talk about and think about model-based systems engineering holistically and independent of languages, frameworks, and tools. I don't want to get into the languages, frameworks, and tools. Really, my thinking of model-based system engineering is that it was envisioned to transform this document-based world to a model-based world. In this document-based world, we have these diagrams and documents and matrices and spreadsheets, and what we do, these things all are out there, and they're all individual entities among themselves. And now what we have to do, we have to bring these things together somehow holistically and through our own mental models and say, hey, this thing in this diagram represents this requirement in this requirements document, right? Maybe it does, maybe it doesn't, right? So from a model-based perspective, I believe that the model-based system engineering was meant to transform systems engineering away from that document-based approach to a model-based approach where we're able to represent that system virtually within our model, right? We're able to represent the system that we're doing virtually within the model, and that's my perspective. Now, some of you may be saying that, hey, where am I in these photos? Even though some people think I'm in those photos, I swear I am not in any one of those photos. Maybe those guys are much too young for me. So when you think about systems engineering, so before we can think about model-based systems engineering, we really have to think about, well, what's really the dimensions of a systems engineering project? So consider this cube here, this simple cube, as being a system, right? And so this cube has some characteristics and some attributes that apply directly to systems engineering and should give us pause when we start thinking about model-based system engineering. For example, a cube has some sort of width, right? And the width provides insight across the life cycle of the system. That should be important to us because systems engineering is a life cycle discipline, right? We care about the system from cradle to grave, essentially, right? From concept to disposal. So it should be important that we're able to represent the entire life cycle within that system. Right. That system, the cube also has height, right? And that height provides a decomposition of our system from the highest level to the lowest level, from the system to the part. And decomposition is something that we do on the left-hand side of the systems engineering V, and this is something that, as systems engineers, we should be familiar with and comfortable with as we're working with our systems. So, again, this cube represents the system, but within that cube is the decomposition of the system all the way down to subsystems, to assemblies, sub-assemblies, components, and eventually to the parts. This cube also has some sort of depth, right? And when I say depth, it has has complex relationships. It has relationships between systems and system elements and functions. It has relationships to requirements, has relationships to risk, has relationships to cost. So has all that stuff that that we worry about as systems engineers. Now, cubes only represent one time, right? Virtually, it's only represented one time. So we should be able to represent all this stuff in that cube one time, and that's why I believe we should be doing from a model-based systems engineering perspective. Now, I mentioned the definition, the INCOSE definition, circa 2007. Now, things have progressed, and the model-based system engineering world is probably the aspect of systems engineering that's making the fastest transition or the most transition over the last 12 years. And I believe it's time to change the definition a little bit. So here's the definition. I mean, whether you like it or whether you don't, I mean, it's a definition I posed a few years ago. It's gotten some traction. It's been a few IEEE papers at this point. It's been presented at the INCOSE IS last year. So it's getting around. I'm not saying it's the de facto standard, because it's not, but it's starting to become popular. And this definition looks at model-based system engineering from the life cycle perspective, which we should be always looking at things from the life cycle perspective as a systems engineer. When it has four components, right? And the four components are the modeling languages. So model-based system engineering should be based on some language. Should be based on structure. We'll talk about structure in a while, but I think structure is the one piece that we miss in model-based systems engineering almost consistently. We should have some sort of presentation framework. We should be able to represent this data that we're working on to the decision makers, so the decision makers can use that data to make decisions. I mean, that should be the purpose of systems engineering, not just for creating the products and the artifacts for the sake of creating these artifacts, but because somebody cares about what we're doing and somebody's going to use that to make system decisions. And then there's model-based processes, right? And I argue that these model-based processes could be either static or dynamic. So in systems engineering, we're pretty comfortable with static models, whether they're in document form or whether they're in diagram form. But we don't really focus a lot on dynamic models. I mean, okay, so I'm not saying we don't focus at all on dynamic models, but we often let the heavy lifting for the simulation piece and to derive behaviors to other colleagues in other disciplines. So, for example, like in operations research, for example. So some of you may say, well, wait a minute, you talked about these four different tenets of model-based system engineering. That's why I call them four different tenets of model-based system engineering. But we're not talking about, and I'm going to pause there and I'm going to say, shh, we'll talk about that in a little while, I promise, but we're not going to talk about it right now. So we're going to talk about these four tenets right now. So what happens in a model-based system engineering environment? So today, what happens is we have these model-based processes. We've had model-based processes for as long as our discipline has been around, right? So we have these model-based processes, and everybody has different model-based processes. And I don't care what your model-based processes are. If they work for you, they work for you, great. But what happens today, we use these model-based processes, and we create these different artifacts with them. Right? We create these different artifacts. And it's important that we create these different artifacts because hopefully these different artifacts are meant to inform and inform decisions and be thought pieces for decisions, or the driver for decisions. But what happens is we use these model-based processes and we create these different artifacts. In the past, we would use Visio or Microsoft PowerPoint or maybe Word or Excel, right? And today, what do? We create these things in a model-based system engineering tool, and you pick out the model-based system engineering tool that you want, using language that tool is based on. And what do we say? We say, we say, hey, that's a win. We're in a model-based system engineering environment. Meanwhile, all we're doing is using these model-based system engineering tools as a rather expensive way to create these things that we used to do with Visio, PowerPoint, Excel, Word, right? So that's how we do things today. And the way we do things today, we often ignore the structure, and the structure is inherent in every one of the tools, whether it's based on a language or based on something that the tool manufacturer and the tool designers have to put in to make the tool actually work, right? So I argue that we should be using these model-based processes, and we should be using this tool, and we should be creating a virtual representation of that system, using whatever language you want, using the structure, whether the structure is inherent within the language or whether the structure is just within the tool, right? And from there, from that virtual representation, we're able to get these different, we're able to view the data in the way we want to present to decision makers so they can make decisions based on our data for how to move the tool, how to move their system forward. So one thing we don't talk about in systems engineering very often, but I think it's important when we start talking about model-based system engineering, and that's the principle of concordance, right? And concordance is the ability to represent a single entity such that data in one view or level of abstraction matches data in another view or level of abstraction. We're talking about the same exact thing. So take for example, this aircraft, the F-A-18, Navy F-A-18, right? So this aircraft is represented one time, right? If I was to represent this virtually in a model, I'll represent this aircraft one time. Right, but I would look at it from all the different perspectives that I have to address on, because the aircraft only exists once. So for me, as a surface warfare guy, I look at the aircraft, and this is what I see. I look at it from the operator's perspective, right? If I'm the designer of the aircraft, or if I'm the maintainer of the aircraft, I'm probably going to have a different view of that aircraft. I'm going to look at that aircraft from the systems perspective. If I'm the weapons person for this aircraft, I'm going to get a different perspective. I'm going to look at things a little bit differently. And if I'm the system analyst for this aircraft, I'm going to look at things a little bit differently still. If I'm the controller for this aircraft, I'm going to say this aircraft is dollar signs. And if I'm the member of Congress, I'm probably going to look at this aircraft from the perspective of how many jobs in my district or how many jobs in my state came from this aircraft. The aircraft's only represented one time, but we're able to capture these different attributes and characteristics of the aircraft, and we're able to do that just in a model environment without having to go to several different diagrams and documents and spreadsheets and then cobble it all together in our minds with our mental model. And I'm not trying to diminish any work that anybody does, but we bring things together and we make conclusions based on that. So I believe that concordance is one area that model-based system engineering, we have to start talking about concordance in model-based system engineering and engineering as a whole. So we're going to talk about the four tenets. I mentioned the four tenets earlier. Briefly, I'm going to talk about them a little bit more in detail. So first one's modeling languages. So the modeling languages serve as a basis for tool development. The modeling languages, they come in a couple different flavors. They could be a visual representation, they could have an ontology, or they could have both a visual representation and an ontology. So when I say ontology, some people say ontology, some people don't like the term ontology, some people want to say meta model. I don't care what you call it, right? I call it an ontology, but in my vernacular, the term ontology and the term meta model are synonymous. And what that ontology is, it's a collection of standardized define terms or concepts and relationships among the terms or concepts, and the relationships among the terms or concepts, and to be able to define that is something that we're going to need in the future discussion when we, future of this discussion when we talk about structure. So when we talk about an ontology, typically popular modeling languages address only one aspect of the information needs. What's really needed, and this is, I think this is an important discussion as we move into defining SysML 2.0, right? That desires to have that long-sought ontology. I think the ontology is something that we need to work not only in SysML 2.0, but as a whole within in the systems engineering community. What are the terms, and what do those terms mean, and how do we represent those terms in systems engineering? What are those fundamental things that we have to worry about in systems engineering? And it should all be in our vocabulary as we go forward as systems engineers. The ontology, I believe, should be simple, right? And we should be able to reduce everything back to its atomic level of elements. So what I mean by that is, if I use the analogy of the English language has somewhere between 500 and 600,000 words. Okay, so now as a person who speaks English, right, I probably use a very, very small subset of those words for my vocabulary, right? And the rest of the words that I don't use, they might as well be non-existent to me because I just don't use them, right? So if you think of an ontology, and if you have a large ontology, think of the DODEF Meta Model 2.0 has almost 600 different terms for that ontology. Okay, so now if I have a large ontology like that, now when I'm the engineer, what am I going to do? I'm probably going to go back to my analogy of using the English language, and I'm probably going to select the 20 or 30 terms that work best for me. Now, if you're using a different 20 or 30 terms that work best for you, we're going to have a problem when we start trying to bring our systems together, because those systems are probably going to have some, you're using different words than I'm using, right? You're using different terms, you're applying different terms to a modeling perspective than I am. And that's probably going to lead to problems. So I argue that we should have that simple ontology. That ontology, each entity within an ontology should have, in my mind, a corresponding visual representation. Some languages out there already do. They have their entity name, and they have a related visual representation. I think with SysML 2.0, I think we'll have an entity, and I think we'll have a visual representation. We already have the visual representation within SysML 2.0. I think we'll be able to tie those two together. We also should be able to define the structure, right? We also should be able to define the structure of the relationships. The relationships help us to define the structure. So when I talk about structure, I'm going to move on to structure. Structure defines the relationships between the system entities. It allows us to establish concordance within the model, and it allows us to see how the emergent behavior materializes, so we can look at system performance, right? So if I think of structure in a real-world system, the structure is not only the building blocks, but the structure is also the relationships that form that complete and functional entity. That should be the same when we're talking about a model. If we're going to have a virtual representation of our system, then we should be able to have those building blocks, and we already have those building blocks. We already talked about those, the diagrams, the documents, and the spreadsheets, but we should have those relationships between them. So, so if we have this, then we understand how each of the elements are connected with each other. And you say, well, wait a minute, Warren, you just said these entities within your ontology are going to be rather simple, right? So how do I represent complexity with only just a few entities, right? Well, the structure is really where the complexity comes in, because it talks about how different entities are related to different other entities. So, for example, down the lower right-hand corner, the larger matrix is a 12 by 12 matrix, right? And there's 12 entities there, and the 12 entities basically are related to almost everything else. So there's not quite 144 different entities there, relationships there, but it's close to it. This helps us to understand. This helps us to establish the concordance. This helps us to understand behavior. Helps us to understand traceability within the system. So, if, for example, if we have a requirement, we're able to see where that requirement is related to in the system without having to look for that requirement and compare that to this diagram, or look at requirements at the various levels of the requirements hierarchy, if you have a requirements hierarchy that you work with, which we typically do. So you're able to look at that requirement just one time, and you're able to see everything that is involved. Be able to show you what it does, what capability it addresses, what system element it has is related to, what function it does, what risk it has. So we're able to make those relationships. And I believe that going forward from a systems engineering discipline, I believe that understanding the system structure is going to be one of the fundamental core competencies of the future systems engineer. Not only understanding system structure, but how to represent that structure in the system. I think if we're really going to move forward with model-based system engineering, I think that's an essential element moving forward. Next one's modeling processes, right? So, modeling processes provides an analytical framework to conduct an analysis of the system virtually defined in the model. These processes could be the traditional process that we have, right? The traditional system engineering process, such as like architecting and requirements management and risk management, but it could also include other areas. And I'm a big fan of being able to say, okay, well, we have this model-based structure at this point. How do we bring other disciplines into it? So, for example, we in systems engineering, we're good at creating these architecting and the requirements and the risk, but I think we do like a rudimentary job when it comes to modeling and simulation, right? So, but who does that? Who does that really well? Our operations research colleagues do it really well. And what I find is talking to both systems engineers and to operations research people, they are trying to address similar, if not the same, problems. And the operations research people are working with one data set, and the systems engineering people are working with another data set. Maybe those two data sets are similar, but they're not exact, right? And I think by opening ourselves up to building bridges with other communities, then I think it would be advantageous. So, for example, look at analysis of alternatives. So, not sure if any of you have ever worked on a typical DoD analysis of alternatives working group. I have in the past. And what happens is you have this working group, in the first meeting, you get together and everybody's there. You have the performance guys, you have the risk guys, you have the cost guys. They're all in the meeting, right? And then what happens? We all go off on our sub-working groups, and the performance guys work with the architecture and figure out what the performance of the systems is projected to be. We're trying to forecast that. The risk guys go off and they do their thing, and then the cost guys, they go off and do their thing. And then at the end, we all come back together and we brief out our results. And you can't sit there and wonder and say, hey, is the system that these guys are reporting out on the performance the same system that these guys are addressing the risk for, the same system that you're addressing the cost for? And the model-based system engineering framework allows us to ensure that when we talk about a risk, we're talking about a risk that can be traced back to the architecture, that can be traced to a cost, or it would be traced back to some sort of performance issues. So when we talk about model-based processes, model-based system engineering really requires an emphasis on the model, specifically on the objects and relationships it contains rather than the artifact. So the artifact is important, because we aren't doing this for ourselves, we're doing this to inform decisions. So it is important, but really our focus should be on the model. Again, we should be able to include other disciplines in model-based system engineering, to include system architecture, to include operations research, program management, classical system, and other classical system engineering. There's also a need to educate stakeholders. So educate stakeholders on the value of model-based system engineering. And when I say stakeholders, I mean primarily non-system engineer stakeholders, because what model-based system engineering is going to do, it's going to provide different insights to them that they may not have today. So there's a few of us from Naval Postgraduate School, and this year we're looking at how to conduct a model, how to conduct a major milestone review in a model-based system engineering community. I know there's some online today that have probably done that, and what we're looking at. So what we're looking at the Naval Postgraduate School, we're looking at the different entrance criteria for different reviews. And we're saying, how do I represent this in a model-based system engineering environment? And oh, by the way, if I have things in a virtual representation, what kind of other information can I glean from that I would not be able to glean by having a stack of documents that are reviewed or viewing a PowerPoint presentation? So I think that is an area, I think when we start talking about model-based system engineering, having stakeholders understand what we're doing, having system engineers work in a model environment, and having the stakeholders think in that model environment or think from a system holistically, I think would be a huge step forward for us. But I do argue that model-based system engineering does require a mindset change, and so we're going to have to change our processes and change the expectations of the different information we're going to provide. Information is important, and presentation frameworks, I think the systems engineering community has done a tremendous job with when it comes to presentation frameworks going back to 1987, the Zachman framework, and evolving into DODAP and MODAP and the NATO architecture framework and now the unified architecture framework. And what these frameworks allow us to do, they allow us to give us some sort of rules and some sort of banning, if you will, of different ways to look at the data, which I think is helpful. However, what I do find interesting is if you look at all these frameworks, they all seem to be geared towards system architecture, right? There's a lot of system architecture stuff in there. But what about these other areas, other disciplines that have something to say within within the system lifecycle, right? What about the system engineering? I mean, so we talked about system architecture a lot, but what about system engineering? If I go to, so for example, if I go to DODEF, I don't see any cost data. You know, I see some schedule data now, right, under DODEF 2.0, but I don't see risk in there. What about program management? So program management, you can't forget those guys. Those guys are a close cousin when it comes to developing a system. You know, what information do they need, and how can it all be incorporated into this virtual environment? So, so typically the modern languages talk about, you know, one aspect of the information needs. We're good at providing you know, architecture data, you know, in our languages, but we're not so good at always doing other aspects of the data that will represent everything else. So I think we need to relook at this as a community. I think provide so we can provide different definitions and reference and guidance. You know, if you look at DODEF, for example, and I try to extend DODEF to say, hey, wait, I don't have everything I need in there. Where's my risk stuff? Where's my performance stuff? Where are my requirements in there? I can't come up with a good answer. So we have to be able to look at these presentation frameworks and figure out what information is actually needed as we go forward in a model-based systems engineering environment. So we should be able to include the architectural data requirements, even V&V data, right? How are we going to test it, the test matrix and stuff like that. So I think this would help a lot, would help us especially address complexity. I think presentation frameworks as they exist today, if we did nothing with them, I think they helped us a lot with binning the models, you know, putting the models into specific categories. I can't say the R words, or I would say the R word, characterizing, I think. Oh, look at that, I said it. And that helped to reduce the complexity, but I still think some work needs to be done there, and I think that's something we could work on from a model-based system engineering perspective. Now this other one topic. Okay, so I said earlier, told you guys who were asking, who had the question in your mind about tools, when I showed the 4 tenets of model-based systems engineering, I said I would talk about it later. I'll talk about it briefly now. The model-based system engineering tools are general-purpose products that use a modeling language, and they support specification, design, analysis of various system representations. Here's some of the tools. Maybe I don't have your favorite tool. I'm not trying to discriminate or leave anybody out, nor am I trying to show favor to any one particular tool. Because as a government guy, I'm not a tool salesman, and I also realize that common tools go, right? So today, the tool I used 10 years ago as a chief architect isn't the tool that I would use today. In fact, the tool I used 10 years ago as a chief architect, I don't even think is supported anymore, right? So when we think about model-based system engineering, we should really be thinking about things tool agnostically, but as we're thinking about a tool, we should be thinking about the 4 tenets of model-based system engineering. So, some people call me, some commands call me, and these organizations, and they say to me, Warren, we want to create this model-based system engineering environment. We want to have a tool study, or what tools should we use, right? Well, if you're going to go have a tool selection for a model-based system engineering environment, I think you should use some of the questions from the 4 tenets of model-based system engineering, because, you know, I could come out and I could say, go use tool XYZ, or they could select tool XYZ, but is that really the best tool for them? So we have a paper coming out during another forum in April, and we started looking at myself and a colleague, they started looking at, okay, what are the different criteria that we should worry about when we start looking at model-based systems engineering. So one of them is what is the technical knowledge of the systems engineering systems engineering staff when it comes to modeling languages? What impact is that language, implementing that language, going to have on the productivity? And does the organization already have a preferred language? If we look at model-based processes, you know, what are the engineering and analysis objectives for this model? Right? Are we modeling the full life cycle, or are you going to model something less than the full life cycle? And here's another thing we don't talk about as systems engineers and in model-based systems engineering environment a lot. What processes are needed for the verification and validation of the model? And structure. How long is the organization willing to migrate to a true model-based system engineering environment where the system is represented virtually instead of via documents and diagrams and spreadsheets? Are we willing to move that? And does a metadata of the system already exist? And finally, from a presentation framework, what are the perspectives or viewpoints do the stakeholders represent? What additional viewpoints or perspectives are required to give the stakeholders everything that they want? And it's probably just beyond UAF or DODAF or the Zachman framework. That's model-based systems engineering demystified. I think by representing the model virtually, I think that will put us on a footing to expand model-based system engineering in the future. I think model-based system engineering, it's an exciting time to be a system engineer working in model-based system engineering. And I think it's going to be that way for the foreseeable future. But we have to be able to migrate. We have to be able to say, okay, here's how our discipline's evolving, and migrate with it. So when we talk about model-based system engineering, it has to be more than just system architecting. We have to consider the programmatic stuff. We have to include requirements in there, right? We have to include the physical features of the system in there. Some tools do this rather well, other tools not. We have to look at the parametric piece in there. So I know the parametric piece is part of different languages, but we have to be able to include different data from numerical analysis in there. And eventually, I think we have to get to the point where we have some sort of relationship with computer-aided design. I know there's one or two tools out there that are looking at computer-aided design, but I think it's really powerful if we go within one environment. I'm not saying one tool, but we go in one environment and we can do everything from the concept all the way down to the design, right? Today, what happens is we have our systems engineering models, and I admit that my knowledge is often limited to the Department of Defense, and we finish all these engineering stuff, and what do? We throw them over the wall, and then somebody else picks it up and puts it into computer-aided design. So I think there's a disconnect there. I think it would be helpful if we could figure out a way to move that forward. So model-based system engineering has a lot of benefits. It helps us to focus on the vision. It helps us to make sure the stakeholder needs are clearly met. Helps us to manage complexity, which is huge. Helps us to manage change. Helps us to support decisions, and it helps us to identify these critical gaps or details that may be missing from just reviewing documents, having it from a document-based perspective. So I think implementing a true model-based system engineering environment requires a leap of faith because it deviates from the analog processes that we're used to today. So I think if we're going to be truly successful, we have to really have to replace the traditional systems engineering processes and models or artifacts with this virtual representation. This requires a culture change. Okay, it's not easy. It requires a culture change. I think we also have a lack of understanding about the definition of a true model-based enduring environment. I think the INCOSE definition could be updated. You know, like I said, it's a fast-moving discipline with regards to model-based system enduring. And I think since it's a fast-moving discipline, I think we have to be able to change with the times. I believe that a comprehensive ontology is needed to do all this and to have this virtual system representation. And we have to be able to have that ontology that defines the relationships and structure so we could have concordance. So that's model-based system engineering demystified. I appreciate everybody's attention today. I appreciate you attending, and I thank you very much.
Warren, thank you for a great presentation on model-based systems engineering demystified. We have a number of questions that have come in, so I'll work through them now. The first one is actually a simple one from Jay Goldman. Will these slides be available for download after the event?
So I can make them available to download. I mean, Andy, you could tell me. I can work with. I will work with you, Andy, and I will figure out a proper place to place these slides, and so everybody
can place them with the webinar recording. If you send me a PDF of the slides, that will work very well.
Yes, that's a simple question, and it's a simple solution.
Okay. Next question is from Chris Hoffman. Is not the structure a part of the modeling language rules in SysML, for example, or are you intending this structure to be a bit more specific, such as meta-models of systems? And he mentions the pattern-based model-based systems engineering working group.
I would argue that the structure has to be more holistic. I acknowledge that SysML does have some structure to it, but I think it has to be more holistic than what SysML has today. I'm hoping SysML 2.0 is going to have a lot more structure. So we have to be able to represent, we have to be able to make those relationships between systems and functions, for example, within the model. And we should just be able to represent one time. So if I change it one place in the model, it's going to change, it's only going to change one time, but every place I need to represent it for my stakeholders in the form of some sort of view or artifact, that change would be made. So I hope that answers your question, Chris. Thank you.
Next question from Jim Teef. Do you have any return on investment numbers to justify model-based engineering to decision makers?
That's a great question. I do not have that. You know, like I said, it does require a leap of faith. The problem is I see a lot of people, a lot of organizations, they attempt to do model-based system engineering. They go in there half-heartedly, if you will, and as a result, it doesn't work out as they intended, right? I think model-based system engineering is oversold in some cases, and when it doesn't work as intended, it gets a bad name.
So, question from A. Long. Is business process modeling inclusive to or a subset of model-based systems engineering?
I would say that business processes would be a subset of model-based systems engineering. So notice I left the definition of model-based systems engineering fairly open so other disciplines and other methods could join.
So, question from Daniel Totham. How have you handled moving MBSE tools over long periods of time, decades, when one used previously becomes obsolete? Risk is we lose our model and its data for a system modeled 10 years ago.
That becomes a huge problem because today, if you look at tools today, a lot of tools out there, a lot of tool vendors will tell you that they can accept other tools, they can share data with other tools, but in reality, it doesn't often work out that well. I think having a common ontology, if the systems engineering community could come up with, could develop a common ontology, and I don't care how that ontology is represented in different tools will have different features depending on what the vendors want to put in their tools. But if we had a common ontology with common relationships, I think we would be able to go a lot further with sharing data, and that includes not only sharing data, but migrating data. And so you want to talk about the cost, right? So the previous question was on the cost and return on investment. When one tool becomes obsolete and unsupported, it's often difficult to jump to another tool without redoing everything, and that becomes a huge problem.
A question from Patricia Lothrop, which has just jumped on me. Where does data governance or data modeling fit in model-based systems engineering?
Could you repeat that question, please?
Yes. Where does data governance or data modeling fit in model-based systems engineering?
Okay, so I think so there's a lot of discussion on this single source of technical truth. There's been some work, I think, by the folks up in MIT about model curation. I think so when we start talking about model-based system engineering, you start talking about data. There has to be, I think, there has to be a model curator, if you will, and that model curator is responsible for the data. So, I mean, there's lots of issues when it comes to governance, because now I've defined my system, and the management has accepted that system, and they have put that system under some sort of configuration management and the model, and now I have to move forward, right? And I'm still working in that model, so I have to be able to have that gold copy, if you will, and then as I move forward, I have to be able to make those changes and track those changes, and that's a problem. I'm working on a medium-sized system right now, and one of the problems that we're facing is how do we maintain that governance? How do we how do we keep that gold copy? How do we track the changes? And how do we go back to like an engineering change board, right? How do we get to the engineering change board and say, hey, here's the changes that we want to make? So that's a great question. I think the governance piece is something that has to mature along with the discipline. I think the governance piece is going to be one of the key aspects of model-based system engineering that we don't necessarily realize today.
So, question from Chris Barreras here. A general top-level question. What type of projects warrant model-based systems engineering?
I would argue that model-based system engineering does come at a cost. So I think systems where it's not able to easily visualize that system, easy to comprehend that system, and easily on paper or in your mind. I think if you get beyond that, I think you really need a model-based system engineering environment. You know, like I said, it does come at a little bit of a cost. The larger the system, the larger cost. But you know, if I'm designing a new lawnmower, for example, new push lawnmower, I'm not sure I would use model-based system engineering from there. I could, but I'm not sure I would, unless I'm going to use this for the way I'm going to do system engineering overall. So if I'm going to use system engineering overall, I can change my processes. I could get a rather low-cost tool, and I can go from there. So I hope I answered that question.